In this video, I'm going to talk about heat transfer between objects and specifically how we measure that using calorimetry. Heat is energy that moves or is transferred from one object to another. And we can't measure the heat directly, but we are able to get a sense of how it is moving by changes in temperature. Now, temperature actually is a measure of the average kinetic energy or the movement energy of the molecules in a substance. And heat, or this energy transfer, is always going to go from the higher kinetic energy or the hotter substance to the lower kinetic energy or the cooler substance. So heat always moves from something that is hot to something that is cooler. This happens actually on the atomic level through collisions as molecules of one substance collide with molecules of the other, and in that collision some of that energy is transferred, just as if you are playing pool and one pool ball hits another one, you can see the energy, the movement energy being transferred from one ball to the next. So the amount of temperature change that we're going to observe whenever a heat transfer occurs depends on three things. It depends on the amount of heat that is transferred, and that generally depends on how much difference there is between the two objects and the heat contained by the two objects, the mass of the objects in question, and then the specific heat or the way that the molecules respond to heat moving into an object. Not all substances respond to heat moving into it in the same fashion. And so we have this thing called specific heat, which is the amount of heat needed to raise 1 gram of the substance 1 degree Celsius. The international unit, the SI unit we use for measuring energy, heat energy, is joules, but calories actually is the original unit that was used, and we still use calories today for measuring food energy. Incidentally, food calories are actually equal to 1,000 chemistry calories, which makes the numbers a little more manageable. Imagine if your grilled chicken sandwich, instead of being 360 calories, was listed on the menu as being 360,000 calories. So substances that have a high specific heat absorb a lot of heat before you get any change in temperature. And water is an excellent example of that. Our pot over here is full of water, and so the water has a specific heat of 4.183 joules per kilogram per degree Kelvin. And it takes a lot of heat going into that pot of water to make that water change temperature. Whereas if the pot was empty and we're really just dealing with the specific heat of the metal, which is given down here as a specific heat of 1.007 joules per kilogram degree Kelvin, the temperature would change much more quickly in that empty pot. And you know this from practical reasonings. You know that metal by itself changes temperature very quickly. Your car gets very hot in the summer sun, but the swimming pool takes a whole lot longer to warm up. Here's a table that shows some specific heats of common substances. Water, of course, with the high heat of 4.184 joules. Then some of our metals down here, aluminum only 0.902 or lead 0.128. So this is something that will melt very quickly. It doesn't take much heat going into lead to make it change temperature and get warmer. So calorimetry is the way we measure the transfer of heat into or out of a system during a chemical reaction or during a physical process of heat moving from one solid substance to another. And we use the formula Q equals mc delta T to calculate that heat transfer. Q itself is the symbol for heat. If heat is absorbed by a substance, Q is a positive number. That would be an endothermic situation. If heat is released by the substance, then the Q is negative, which would be indicating an exothermic situation. And so negative and positive numbers in the calorimetry formula are talking about how the heat is moving. Is it moving into something or out of something? M equals the mass of the substance. In our laboratory, typically we'd be working in grams, but you also can work in kilograms. And then C represents the specific heat of the substance. The little delta in front of the T means a change in. So the change in temperature would be calculated by taking the final temperature and subtracting from it our initial or starting temperature. So how do we use that? Well, here's a sample problem. It says what amount of heat is needed to increase the temperature of 10 moles of mercury by 7.5 degrees Celsius. The specific heat of mercury is given at 0.140 joules per grams times degree Celsius. And we get this complicated unit so that things will cancel out correctly. So our formula, of course, is Q equals mc delta T. So Q is the amount of heat. We're trying to figure that out. We have 10 moles. Well, what's the mass of 1 mole of mercury? Going back to the periodic table, you'll find that 1 mole of mercury is 200 grams. So we're going to start off with 10 times 200 grams. That will give our moles, the molar mass of those 10 moles. Our specific heat is given as 0.140 joules per grams degree Celsius. And then we are changing the temperature. We are increasing the temperature by 7.50 degrees Celsius. So heat is going into something that's going to be a positive 7.50 degrees Celsius. So you see here, we'll be able to cancel out the grams. We'll be canceling out our degrees Celsius. We're going to end up with joules in our answer. If we go ahead and do the math on this problem, we're going to see that our amount of heat that's being transferred is 2800 joules. So that's the amount of heat that was needed to move into this sample of mercury and raise its temperature 7.5 degrees. A calorimeter is the name of the piece of equipment that is used to measure heat changes. And remember, we can only measure heat transfer by changes in temperature as heat's moving from something with a higher heat to a lower heat. And so you're always going to involve two substances when you're using a calorimeter. Usually the object you're testing and then water. There are a couple basic assumptions that no heat is lost to the surroundings, so every bit of heat that is given off or absorbed by the substance you're testing will be staying within that system, and whatever heat that is lost or gained by the reaction is then gained or lost by the water surrounding it. Water is typically the second substance. A very simple calorimeter can be done in a styrofoam coffee cup. And so you have like a chemical reaction if you're measuring the heat transfer when something is being dissolved. So it's dissolved in the water, but you're actually measuring the temperature change of the water. This fancy piece of equipment is known as a bomb calorimeter, and the substance you're testing is in this little chamber with lots of oxygen, so you have a good combustion reaction going on. But then if heat is given off, it's going to move into the water on the outside of that container, and the temperature then is measured of the water. This is what we do to get calorie counts on food. They are combusted in a bomb calorimeter, and then the temperature change of the water tells you how many calories are in that food. So just like the previous example, you're going to use the specific heat equation to determine the heat absorbed by the water. And as I said before, anything that is absorbed or released by one substance will be equal in quantity but opposite in sign. So as heat is released from one thing, that heat would be given off, so it would be a negative Q value, but it's going to be absorbed by the water in the calorimeter, and that will have a positive Q value. The opposite, of course, is always true. If you have an endothermic process, as we've given here, it's going to be absorbing heat in from the surrounding water, which means the temperature is going to go down in the water. So whenever you're analyzing a problem that's dealing with heat transfer within a calorimeter, it's going to have two steps because you're going to be measuring the heat moving out of the substance and into the water, and then using that value to calculate exactly how much came out of the substance or into the substance if it's an endothermic situation. So our sample problem here says a 100-gram sample of an unknown metal is heated to 95 degrees Celsius. The hot metal is placed into a calorimeter containing 50 grams of water at 20 degrees Celsius. The water and the metal come to a final temperature of 31.67 degrees Celsius. What's the specific heat of the metal? So both parts of this problem are going to depend on our specific heat equation, the Q equals mc delta T formula. And so we're first going to figure out how much heat went out of the substance and into the water. So we're figuring out our heat transfer, our Q, our mass of our water. It's 50 grams, so we would have 50 grams Our specific heat of water, if you remember from the chart 2 or so slides before, is 4.184 joules per gram degree Celsius. And then we have the change in temperature. Well, the temperature of the water started out at 20 and it ended up at 31.67. So in order to calculate the change in temperature, you would have 31.67, our final temperature, and subtract from that the 20 degrees, which is our starting temperature, which gives us a temperature change of a positive 11.67. So we multiply 11.67 degrees Celsius. And then again, our grams are going to cancel out. Our degrees Celsius are going to cancel out. If you go ahead and do the math on all of these numbers, we get an answer of 2,440 joules of heat that went into the water. And you notice this is positive because the heat is being absorbed by the water. So if this is how much heat went into the water, this is our water substance, then that's how much heat had come out of our unknown metal. But because it came out, it's going to be a negative value. So we're still using the Q equals MC delta T, but now we're going to do it for the metal. So I just changed colors here. We know we're going to have a negative 2,440 joules as being how much energy came out of the metal. Now we have to calculate the mass of the metal. So we had 100 gram samples. So we have 100 gram. The specific heat is what we're trying to figure out. So we don't know the C. That's our variable. And then what's our temperature change? Well, this one, again, ended up with a final temperature of 31.67, but its starting temperature was 95 degrees. So you were going to subtract 95 from that, so you're going to end up with a negative number, and this would be a negative 63.33. So that was our temperature change. So we plug in a negative 63.33 degrees Celsius. And then we just solve for this problem. We're going to divide both sides by these numbers, of course, our 100 and then our 60, negative 63.33. That'll cancel out these guys. And over here, dividing by 100 grams and negative 63.33 degrees Celsius. And so the negatives are going to cancel out if we go ahead and do all of this math. You get an answer of 0.385 joules per grams degrees Celsius, which is going to equal the specific heat, or the C, for this unknown metal. So because we're using a calorimeter, this has to be 2 steps because heat is moving between the substance, from the substance into or out of the water. And so we can calculate the water, and then we go on to calculate the unknown metal. Both of these types of problems will be what you'll be doing on your worksheet to get a handle on practicing calculating heat transfers.